Thanks. That's all right. My bad. All right. And so now the idea is to turn in V into a family over something. K has transcendence. Okay? So what we do is we make K. So K is the fraction field of some integral domain R, which is a finitely generated ring now over Q bar. Okay? I'm going to give an example in a second. But first, what we do is we let B equal spec R. So now B is an actual Q bar variety. And K is the generic point over B, is the fraction field of rational functions on B. But B has lots of other points as well. In particular, lots of Q bar points to which we can apply our assumption that Mumford is correct. That's sort of the idea behind the approach. All right, so now we get B equals spec R. And now, by possibly shrinking B a little bit, by removing some sort of bad points, in a way I'm not going to be totally precise about, I'll give an example to illustrate a little bit of what's happening. We can get a variety A over, or scheme A over B, and a subscheme V in A, such that lots of things are true. So first of all, A over B is proper, like projective, smooth, connected. Okay? That's the first thing we want. And so A is going to be like a family of abelian varieties over B, and so what do we want? Well, there's going to exist a sort of an identity section from B to A is a section. An inversion map from A to A, where this is a map now over B, so it's a map commuting with a map down to B. Is this too low? No? Okay. And a multiplication map from the fiber product of A with itself over B to A. Okay, so in other words, for every point in B, the fiber has a multiplication structure, and it sort of varies algebraically. This family, sort of such that these three things make A sort of an algebraic group or an abelian variety over B. Okay? That's the one from the map from A over B. V is even easier. We want V over B just to be sort of proper and smooth. Just want V to be a nice family. So no point where V is missing or anything like that. Okay, so let me give an example of this. Okay. So the general kind of argument is called spreading out. And in sort of any concrete case, it's sort of pretty easy to do explicitly. If you're in the general case, there's like a section in EGA where they do that. They have a general theorem. But let me just give an example. So we're going to stick to one dimension because I don't know about equations other than that. But so E will be the following elliptic curve. Okay, so it's a two-dimensional complex projective space. And then, is it homogeneous this time? Yeah. So in projective coordinates x, y, and z, 4x cubed minus xz squared minus pi z cubed is y squared z. Okay, so it's a perfectly good curve in P2. And note that 1 minus 27 pi squared is not in fact 0. So it is actually an elliptic curve. The discriminant is not 0. Okay. All right, and now P is going to be a point, a complex point on E. That's a one-dimensional variety. And it's going to be the point 1, let me do this correctly, so it's going to be the point 1 root 3 minus pi and 1. I'm pretty sure this is a point. So the squared is 3 minus pi. Here we have 3 and 3 minus pi. So we're all good. Okay. So this is a case to which we could try to apply Riemann and Mumford, which is obvious here because P is a point, so nothing to do. It's either a third point or it's not. Regardless, we can try to make this procedure sort of a little more explicit. Okay, so our field K will just be, we'll throw in all the numbers we need to make all these guys make sense. So K is going to be, we're throwing Q bar just because we might as well, but we can also deal with Q. So we need pi to define the curve E, and to define the point P, we need the square root of 3 minus pi. So this is what our field is as a subfield of the complex numbers. And so as an abstract field, it's Q bar adjoined. So T will act like pi, because pi is transcendental. And then for root 3 minus pi, we adjoin S, and then we set S to be 3 minus pi, root 3 minus pi. Okay? So this is pi goes to T. Root 3 minus pi, the choice of root 3 minus pi goes to S. Okay? Of course, Riemann and Mumford doesn't care how your field is, if it's abstract or a subfield of complex numbers, so we can deal with it just as an abstract field. Okay, and now what's a ring R going to be? So first of all, we might as well make T not a field variable. So we have T and S here, and we'll mod out by this guy. And that'll be enough to define E and P, but we want E to be an actual elliptic curve. We want it to be smooth, which means we need the J invariant not to be 0. So in fact, we're going to make that true as well. So the only purpose of the variable U is to make 1 minus 27t squared not equal to 0. So we just define U to be the inverse of 1 minus 27t squared, and all of a sudden it's nowhere near 0. Okay? So this is R. Okay, and so now, finally, our elliptic curve over R, just to make everything complete, just replace the pi with the t, and this is now a closed subvariety of two-dimensional projective space over R, and our point P is the point 1, S1, okay, which is an R section of E. Okay, so P is a closed subvariety of E, which is an elliptic curve sort of over spec R. All right. So in general, the idea is like the same. In the general case, you make K and R the same way, and you write down all the group laws for A on the inversion maps, and you sort of add in remove as many points as you need, sort of add as many inverses to make all that make sense. And that's what happens. Okay, any questions about this? It's abstract nonsense, but until you're comfortable with it, it's very annoying and difficult abstract nonsense. All right. Okay, so now let's deal with these torsion sections more precisely. Let's start with the torsion points. So, because A is an algebraic group, we have a multiplication like a map for every n. Which goes from A to A, which just sort of says A to Z. But it's a map over the scheme B, right? So it preserves where you are over D, fiber-wise multiplication by n. Okay, so we define A of n to be, so it's fiber-wise just the n torsion points, but to give it a scheme structure, or variety structure, we pull back the identity section E, as we assume that we have. Right? So E is like a section over B, that's more like B, and we pull it back, multiplication by n. Now the multiplication by n map is a tau, so how should we think of this scheme A of n? Well, the map from A of n to B is finite and a tau, and it's a Galois cover. With Galois group point-wise, the Galois cover is Z mod n 0 to G. Okay. Okay, so the scheme A of n does not have to be the variety does not have to be reducible. It could be n squared, n to the 2g copies of just B, or it could all just be one connected component, right? Because if you start with these n squared, n to the 2g, points in a given fiber, and you start looping around, going around loops in B, they could sort of glue up to each other in different ways. So even though the given fiber is not connected, the whole thing could have several like components or just one. So let's break up AN into irreducible components. Okay. And so what acts on these components? Well, it's sort of the action of the loops on the base. And so it turns out if you look about these components, and you just look at it over the generic point k, now we're back to original equivalent variety over k. So here is going to be finitely many points. And in fact, this is going to be, so this is now an original equivalent variety. It's a subset of the torsion points, which are all defined over k bar, because it's an algebraic thing. And this ends up being a single Galois orbit. So I'll call the Galois group GK. Okay. It's defined over K, so it's sort of clearly Galois stable. But if it broke up into two different sets of Galois orbits, you could actually complete them each to reducible components. Okay? So this is a fact. Alright, so in fact, I'll call this the fact. There's a bijection between irreducible components of some torsion sections. Is a bijection with Galois orbits of these torsion points. Okay, so likewise, you could do a correspondence between torsion sections and these torsion points, but we're not going to do that. For simplicity, we'll just stick with torsion points. And for the proof, we don't actually need to talk about torsion sections in this way. So one important thing I want to point out, because I got asked about this last time, is, so if we just started with an arbitrary variety of A, or say even a point of A, then by sort of general nonsense, we could take this point and sort of complete it over B. Except we might be missing some points in B. Might be some points in B where it's not defined. Okay? Just like before it being an elliptic curve, we had to invert 1 minus 27 squared. Likewise here, the coordinates of P might have some denominators. And be missing over some points. But in fact, these torsion points are finite and flat over the entire base B, exactly because they're pullbacks of this sort of smooth operation. So once we have the script A and actual abelian variety over the base, all these torsion sections are globally defined. There's no issue with like completion or anything like that. Okay, so now let's start the proof. So proof of reduction. Okay, so the like 0th step of the proof is assume Manin-Mumford for Q bar. Yeah, at some point we'll use that. All right. So what we're going to do is we're going to let the set of TIs be the so GK orbits of torsion points which are in V. Okay? So we're going to look at all the torsion points in V and group them together by their Galois orbits. Okay? And let the TI be the corresponding subvarieties of script V. Okay? They're inside V at the generic point, they must be inside V everywhere. Okay. So now the next thing we're going to do is we're going to let delta inside the complex points of B, so think of B as an actual variety now. So be an open polydisk. So just a unit ball to the power of the dimension of the unit. Okay? And let A delta be the fiber over delta. Okay, so A delta now is just a purely analytic creature. It's just like it's an algebraic group over delta, but it's an analytic group over delta. It's holomorphic. You can still add fiber-wise, but there's no algebraic structure because delta is, of course, not an algebraic subgrid. Okay? Okay, now the point is that delta is simply connected. So topologically, A delta is a what? Well, it's an S1, sort of this R mod Z, to the 2G bundle over delta. And delta is simply connected. It's a polydisk. And so A delta is homeomorphic topologically, or even real analytically, to delta cross S1 to the 2G. Okay? So this is the point of going to a polydisk, is because now we can identify all the torsion points in all the fibers above delta. Okay? So from this perspective, what are the torsion points? Well, they're really, the torsion sections, they're really easy. You just take delta and multiply with some torsion point in S1. Only the Galois action is present, so maybe you have to take a few of them at a time. But that's really all it is, delta cross some set. Okay, so now what we get for this is for all B inside delta. Well, if we look at the do I even need this? No, let me not do this. Okay, so now let the T sub I, these torsion sections that were in V, we're actually going to write them sort of over delta. If you restrict them to our polydisk, what are they? Well, they're exactly delta cross some finite set S sub I, where Si inside R mod Z to the 2G is a finite union of torsion points. Okay. All right. So now is where we bring in the work we did last time. So last time we showed that if you have any subset, actually, of R mod 0 to the 2G, there's a minimal finite union of torsion sections which contains that subset. Right? So now let M, and this is not my number, this is just some smooth property of studying torsion sections. So let M and R mod 0 to the 2G be the minimal finite union of torsion cosets. Remember, M is a union of closed Lie groups by torsion points. Translets of closed Lie groups by torsion points. Containing all of the SI. Okay. Okay, so here's the part where we're going to apply Mann and Mumford over Q bar. So now, if you take a point B, which is inside your polydisk, and it's also a q-bar point of your base V, of your base B, pardon me, then by assumption, the fiber of V at B inside this abelian variety satisfies Manin-Mumford, which means there's some finite union of torsion cosets with complex structure, which contain all of these SIs. Right? Okay, but sort of what are like these torsion cosets? Well, they're transitive abelian subvarieties. So in particular, they're closed Lie groups. So there are also torsion cosets in this weaker sense, of just being closed Lie groups, closed subgroups of R mod 0 to 2G. Okay, it's weaker. Just like for an elliptic curve, you have sort of real lines which are closed subgroup but have no holomorphic or algebraic structure. Likewise here, you have sort of a lot of extra guys. But it's certainly true that any abelian subvariety is a closed Lie group. So in particular, it has some finite union of closed Lie groups containing all the SI, and so it must also contain M, because M is the smallest such guy. Okay? So therefore, VB, thought of as a subset of R mod 0 to 2G with our identification, contains this subset. Okay? Okay, but q-bar points are dense inside the complex space. And so therefore, since V delta inside A delta is closed, so V delta contains all of delta cross M, contains the fiber of N for every q-bar point, so the closeness is containing all of that. All right. Questions about this part? Yes.
It's really hard when you use this equilibrium construction, like you said, it's something supposedly.
Yeah. So yeah, sure. So what's happening is I've been a little not careful here, because I've been using the word torsion coset in two different senses. One is with respect to just closed Lie groups of R mod 0 to 2G, where it's translated by torsion points of closed Lie groups inside R mod 0 to 2G. The other sense is with respect to abelian varieties, where now you translate by torsion points algebraic subgroups of this abelian variety. Now these two aren't the same. This notion is more restrictive than this one, because you have Lie subgroup, closed Lie subgroups, which aren't algebraic. Just like for an elliptic curve, you have sort of real lines which have no algebraic structure, they're holomorphic. But it's certainly true that every algebraic subgroup here is a closed Lie subgroup. That's all I will say. Yeah. So because you have even algebraic subgroups containing all these S sub I, it must certainly contain the smallest torsion coset in this sense. Other questions? All right. So once you have this, there's lots of different ways to finish. We should have done most of the work. I don't know of any super clean way. So what we're going to do is the following. So let me just mention, what you'd really want to do is get this M over the entire base at once, and then you would prove that that is your sort of maximal torsion coset. That's kind of hard because you can't identify the whole thing at once with R mod 0 to 2G. You have to deal with monodromy, and then you have sort of these loops, and it's kind of hard to see how they act. So I couldn't really present that in a very clean way. So here I think is one relatively clean way of doing it. So now what you're going to do is pick a generic point B inside delta of C. So B is now very non-algebraic. B will be transcendental of transcendent degree, the dimension of B, of big B. Okay? But this is not a generic point in the scheme theoretic sense, it's actually a point inside this complex set. Okay. So then, if you look at VB inside AB, this is a pair of complex varieties now. So there's a pair of complex varieties. And what it is, what is it actually? It sort of is the base change of VA over sort of R under the map sort of B, which sends R to the complex numbers, right? You're sort of evaluating transcendental coordinates of R at B. B tells you how to evaluate it. Sort of like having something over Q adjoint T, and then you set T to pi. That sort of gives this kind of evaluation. Okay, because B is generic, this is an injection, so you can also think of it as the base change of the pair VA over K to the complex numbers under a map induced by B. Okay? So if you evaluate sort of, we have this family of Billian varieties, A, over our base B. At the like actual generic points, which is K, we have our A over K. And then if we evaluate at any other point, which is sufficiently generic in the sort of usual sense, transcendental sense, we get complex varieties, which is the base change of our original pair under a certain embedding into the complex numbers. And there's like tons of these embeddings, right? Because for every transcendental coordinate, you can decide where it goes. So get some random one. Okay, so now what do we know? Well, by what we just proved, all the torsion points of V under the complex numbers, which is the same as the torsion points of V under K bar, because torsion points are all algebraic, are contained inside the closed real Lie subgroup. Inside M, which is a finite union of sort of torsion cosets in the Lie group sense. Let me call them Lie torsion cosets. Yeah, because M is not necessarily holomorphic as far as we know. So now, as soon as we upgrade M to the holomorphic world, then we'll be done. Then we'll know that all the torsion points are contained in finitely many torsion cosets. So that's the M in Montfort. Okay? Okay. Now we need the following lemma. So let me call it G in A be any subgroup, so let me, the complex points of A, be any subgroup. So no assumptions. G doesn't have to be closed or anything, it can be some horrible mess. Then there's the risky closure of G. is also a subgroup, so an algebraic subgroup. Okay. This is also a general nonsense statement, but let's do it. Okay, so here's the hard part of the proof. So we know that the multiplication map from A cross A to A, if you put G cross G here, the image of this lands in G. Let me write it as maybe M of G cross G lands in G, which is clearly inside the Zariski closure of G. Okay. Okay, so now for all G in G, M of G cross G is a G Zariski closure, which means that if you pull back the Zariski closure of G under the multiplication map, this is some subvariety of A cross A, and you intersect with the point G cross all of A, then this contains G cross G. So this has to be an algebraic set which contains G cross G, algebraic variety containing G cross G, and therefore it also contains the Zariski closure of this, which is just this. This variety is isomorphic to G. This set is isomorphic to G, and so the Zariski closure must be just this guy. And what that amounts to is that if you do this, this is also contained closure of G. And so going through the same argument again, you can upgrade it to all of G's R cross G's R. And likewise, the inversion map can be shown to satisfy the same thing, the same argument. And so that's it. It's closed under addition, it's closed under inversion, and so it's a subgroup. Okay. Okay, so now corollary is that M is already Zariski closed. Okay. So proof. So first write M as a finite union of Lie torsion cosets. Okay, where these GIs are closer to the real topology, but maybe not Zariski closed, as far as we understand. And the Zariski closure of M is just the union of Zariski closure of these guys. And you can close before or after you translate, doesn't matter. Okay. So these guys are algebraic subgroups, right? So this certainly is a Lie torsion coset as well. Is that, sorry, a union of Lie torsion cosets. Union of Lie torsion cosets, which contains M. However, by assumption, M contained all the torsion points inside V already. Okay? But the torsion points inside this guy equals the torsion points inside V equals the torsion points in M. And torsion points are dense inside torsion cosets, and so therefore M is already seriously closed. Okay, and so that's the end of the proof. Now we have finite union of torsion cosets containing all of the torsion points inside V. So they must contain all the torsion cosets inside V as well. Any questions? All right. Okay, so that's the reduction from C to K bar. I want to point out, so later in the course, if we have time, we'll do the reduction also for the Bombieri-Mastroianni conjecture, which we talked about 2 classes ago or something. So that reduction has elements in common with this one. So whenever when we look to the K-bar, you want to make some base, you want to spread out, you want to apply your conjecture to the K-bar points, then you want to see what you conclude for the entire family. The reason that it's substantially easier here than for that conjecture is because if you think about it, what does this say? Well, this talks about the torsion points that are already sort of contained in V and the torsion cosets that are contained in V. Whereas Bombieri-Mastroianni conjecture talked about sort of torsion cosets intersecting V atypically, right? And so the issue with doing this kind of proof, at least with doing it naively, is that at every Q-bar point you may have a more and more complicated torsion coset intersecting V. Then you have to sort of think about whether you can interpolate that to get something for complex numbers. And so it's worth sort of going through the same kind of proof and seeing where that proof becomes harder. Okay, let's start the next. Okay, so let's start on the next topic. Now we're going to prove Munn and Mumford for Q-bar will be the next thing. And so we're going to take an equidistribution approach, so a similar approach to what we did for length conjecture, but it's going to be harder in this case. So let's start with just discussing the monodromy action of the Bealing varieties. So let A over K, where K is any field, be an abelian variety of dimension G. And should we, well, I guess let's assume the characteristic of K is 0 for now. Okay? So as we saw, if we look at the torsion points of A, they're all over K bar. And they're isomorphic to Q1Z to the power of 2P. But to define it with K bar, use 1 over K. And so what we get is a map for the Galois group of K bar over K, Ck, to the automorphisms of the abelian group Q mod Z to the 2G. So what is this? Well, it's just the union of all the m torsion points. And so this automorphism group is just the inverse limit over n of the general linear group of Z mod n Z. Okay? And what is this inverse limit? Well, it's just the general linear group of Z hat. You can take this inverse limit inside, which you can also think of as general linear group of all the p-adic integers. You can separate them all out. Okay? Okay, so it's often important to us for these questions that sort of Galois orbits are very large. And what is Galois orbits being large equivalent to? Which is actually equivalent to this map having large image. You want this action to be sort of as big as possible in some sense. So I want to mention that if you throw in the notion of Weil pairing and they'd be in varieties, so some sort of symplectic pairing of the torsion points, and you can get this into a smaller group, sort of a type of generalized symplectic group. But we're not going to talk about that.
So can I ask you a little bit about what you raised?
Oh yes.
There's a very final argument. You said that like M and its Zariski closure have the same torsion points.
Yes.
And therefore they're the same because torsion points are dense or always.
Yeah, they're both unions of Lie torsion cosets, right?
Yeah.
So if you take any closed subgroup of R mod Z, the 2G,
Yeah.
there's just another sort of torus in there,
Yes.
and the torsion points are dense in there,
Right.
like just under the usual topology.
Mm-hmm.
And M and the Zariski closure of M are both closed.
Okay.
So they both contain the same sort of torsion points, and so they're both equal to just the closure of the torsion points.
Oh,
inside.
okay. M is okay.
Mm-hmm.
M is closed.
Yeah, M was closed. The lemma was for a general subgroup G with no properties. But if you recall, M was actually like a Lie torsion coset
Right.
union.
That was.
Right. Yeah. To be honest, for the end of the argument, it doesn't even matter if M is the closure of M. You could just conclude by saying that the closure of M contains the torsion points and you're done. But it's nice to know you've already constructed it. All right. So let's isolate out one prime at a time. And so a convenient way to do that is you can define the Tate module of A to be just the inverse limit of the p to the m torsion points of A, where the transition maps a multiplication by p. Okay? So this is the p-adic Tate module. And so if A were actually defined over C, an easier way to think about this is the Tate module is just a homology tensored with ZP. Okay. But if it's not defined over the complex number, it's sort of a more concrete way to think about it. And then sort of this map. So I call this phi k. I wanted to call it phi a. Phi a, written this way, is just the product of these maps phi a p infinity, where phi a p infinity is a map from the Galois group to the automorphisms of the p-adic Tate module. Okay, so let's stop here. Next time we'll sort of explore more about these representations. Yes?
Should it be the other way around? Like 8 should be 10 minus 1, 2, 8.
No. It's this way.
Precisely.
Yeah, I know. So if you're doing the way you were describing, what you would get is just the p power torsion points of A, just under inclusion. We want something that's p-adically complete. And so you really want it this way. So points here are like inverse systems of p to the m torsion points, which map to each other on multiplication by p. Questions? All right, see you next time.